Hello everyone, we have chosen the topic dynamic Bayesian networks for the presentation. Here's a team comprised of Punarjeet Singh, Nikhil Tailor, and Pushpendra Singh Champawat. So before starting with Bayesian network, let's see first where it comes from and what its roots are. The Bayesian network comes from the concept of Bayes' theorem, which describes the probability of an event based on prior knowledge of conditions that might be relevant to the event. Bayesian networks are already well established representation of domains involving certain relations among a group of random variables. In more of a mathematical terms, a Bayesian network is a graph, to be precise, a directed acyclic graph or DAG, in which each edge corresponds to a conditional dependency and each node represents to a unique random variable. If we go and look upon our journey example, where we have four nodes, namely cloudy, sprinkler, rain, and wet grass, which represent the situations of a cloudy weather, sprinkler in the grass, if the rain has happened or not, and the final output wet grass. So if we see initially the probability of having cloudy day is 0.5 in both cases, it is true or false. But this thing is further what happens. The next two things, sprinkler and rain, are dependent on the weather. So sprinkler, if there it's a cloudy day, the probability are very less as compared to with the different in the other case it reaches to zero point 0.9. Similarly, if there's a cloudy weather, obviously the probability of rain is zero point 0.8 and false for zero point 0.2. But the main question is the wet grass. If both the things, sprinkler and rain, are true here, the resultant truthness of wet grass is 0.99 as compared to last case, both are false, which tends to 0. So if there's no rain and sprinkler is not open, obviously the wet grass we couldn't find at the end of day. Also, the Bayesian networks satisfy the local Markov property, which states that a node is conditionally independent with its non-descendants given its parents. If the adjoint example, we click on this property and see if it satisfies or not. See, the wet grass is only dependent on sprinkler and rain, but the cloudy weather is not directly depending the wet grass. If we move on further, the Bayesian network models for dynamic processes. There are two kinds of state-based and event-based. The state-based models represent the state of each variable at discrete time intervals so that network consists of a series of time slices where each time slice indicates the value of each variable at time t. Dynamic Bayesian networks, which we will discuss further upon. The other one are event-based models, which represent the changes in state of each state variable. Each temporal variable will then correspond to a time in which state change occur, event networks or temporal networks. So basically, in the first case, we're more focused on the time slice intervals. In the second case, how are the state variable changing over the time? So what are dynamic Bayesian networks? Generally, most of the events we meet in everyday life are not detected based on a particular point in time, but they're just instants. But if we can be defined to multiple states of observation that yield a judgment of one complete final event. Time is also an important dimension in the field of AI and reasoning. However, Bayesian networks do not provide any direct mechanism for representing temporal instances. Statisticians have developed numerous methods for reasoning about temporal relationships among different entities involved, and this thing is known as time series analysis. So we'll discuss how they deal with our dynamic Bayesian networks. As we discussed earlier, we get dynamic Bayesian networks through an extension of Bayesian networks to model dynamic processes. A typical dynamic Bayesian network consists of a series of time slices that represent the state of all the variables at a certain time t. For each temporal slice, a dependency structure between the variable at that time is defined, called the Bayes network. Additionally, there are edges between variables from different slices, with the directions following the direction of time, defining the transition networks. The nodes here are a set of random variables, whereas if a direct link exists between the two of nodes, it's known as the direct influence. Also further, we have CPTs, the conditional probability table for each node. The dynamic model do not directly be observable, but they may be influenced some other variables that we can directly measure or calculate. Like the state of some state system needs not to be unique, simple state. To discuss further, I would like to hand over the presentation to my friend Nikhil so he can conclude from there.
Thanks, Pushpendra. Now, let us consider an example of dynamic Bayesian network. Let us consider at a time instant at t, there is a variable we denote it by xt. There is a state which we denote by st, and what we infer from that state at time t is denoted by et. Now, we consider in a time instant of t plus 1. Here, the variable is denoted by x at time xt plus 1, state is denoted by st plus 1, and what we infer from that state is denoted by et plus 1. Now, here arrows denote what denotes the dependency of that variable. In this case, consider the case of xt plus 1. Xt plus 1 is dependent on a variable at xt. Hence, there is an arrow from xt to xt plus 1. State at t plus 1 is dependent on the variable xt plus 1, xt, and st. Hence, it is denoted by an arrow. And inference, what we conclude from st plus 1 is denoted by et plus 1, and there is an arrow. Similarly, this we can do in other time steps. Now, coming to another slide, in the dynamic Bayesian network, there are some assumptions that we follow. In first order Markovian model, the state variable at time t depends only on the state variable at time t plus 1 and other variables at time t. Suppose there is the paper we have is wet, so it is dependent on whether there is at t minus 1 there was a water on that paper or not. So it is this kind of condition is denoted by first order Markovian model. In the case of stationary process, it states that the structure and the parameter we choose for dynamic Bayesian network, and they should be constant, but means parameter number of parameters should not change, but the values of parameter can change, and structure, it should not change much. There should not be any much change to the structure. We cannot add new structure in the process. Now, coming to the next slide. In the case of dynamic Bayesian network, dynamic Bayesian network can be seen as a generalization of Markov chain. Here, in Markov chain, we consider variables x1, x2 at time t. The probability of getting x1, x2 up to xt is denoted by probability of x1 and probability multiplied by probability of x2 where x1 has happened, and similarly we can goes on multiplying till we get probability of xt, where we have got given probability x of t plus 1 has already happened. This kind of probability distribution is denoted by is can is denoted by Markovian chain. In case of hidden Markovian method, we introduce a new variable which is defined by s. S defined a state at that time t, and y denotes the variable on which state s depends. Here, the probability of uh, state and variable from 1 to till the time t, and variable y from 1 to time t is denoted by probability of s1 into probability of y when given s1 has already happened, and is from this inference we can keep on multiplying, and we get a probability of uh, getting that state and variable at time t in that state. Similarly, for Kalban filters, it is an another algorithm here. In Kalman filters also have one state and one observation variable, but both variables are continuous. In this, the basic Kalman filters assumes Gaussian distribution and linear function for the transition and observations. Now, coming to the next slide. Inference is denoted by what we infer from the state and variables from that at instant time t. In inference, efficient inference method had been uh, developed till now, such as hidden Markov models. It's in process of inference, its complex computational power increases as we increase the complexity of model. If we keep on increasing the complexity of model, then computational power used for the inference would increase exponentially. Here in inference, we can take suppose we have a large data and we want to bring a model which can predict at time t or t plus 1 what will be the output or probability of the output. Here in this case, we can approximate that by taking a sample. We can take a sample and develop a model of inference on that sample, and we can apply that model, and also we can predict what will be the probability of that state and time at that at time in future. Now coming to the next slide. There are different type. There are four type of inference models we uses in dynamic Bayesian network. First one is filtering. What is filtering? In filtering, we predict the next state on the past observations. At time t plus 1, just immediate next probability of the event and variable we do not we predict it from past previous observation that we have taken. Now in prediction model, we predict the future n models. Means suppose for example a, a, a car is running at a time with an acceleration. Now, if uh, a car is running at time t, if with velocity v, and we want to predict what will be the probability that its velocity and its state at time t plus n, we can also predict it, and this using this prediction model. Similarly, we can use it this model in the prediction. Now coming to the next slide. This slide is will be presented by Punarjeet.
Okay, thanks, Nikhil. As we have seen two types of inference of Bayesian networks, now let's see what smoothing is. So let's consider a window of size t. Then smoothing refers to the calculation, the probability of calculating the random variables given the observations of the past, the present, and the future. In filtering, we were only considering the past observation, but in smoothing, we consider the past, present, and the future. So mathematically, it can be written as the probability of the random variables x at timestamp t given the observations from the timestamp 1 to the timestamp t. So let's move on to the decoding. Now, what decoding is? So as the name suggests, we need to get a value of these states. So a state can be represented as these random variables from x1 to xt. Now we need to find the probability which maximizes the current state. So we will get some values from 1 to t, and we will maximize this to get the decoded sequence, which determines that this is the most likely sequence of the hidden variables given the observations from the timestamp 1 to timestamp t. Okay, so let's move on to the next slide, where we will be discussing about the structure and observability. These are the two important features of dynamic Bayesian networks. So let's see how dynamic Bayesian networks are constructed. So as we can see in the adjoining figure, we have X, S, and E. So this is the base structure. How X are the hidden variables, S is the state, and E are the observables. So we can see this as a Bayesian network only without the timestamps. So the base structure we can see as a Bayesian network. Now let's see it at the second diagram. We have xt, st, et as the random variables at timestamp t, and xt plus 1, st plus 1, et plus 1 that variables at timestamp t plus 1. And we have some dependencies from xt to xt plus 1, st to st plus 1. What we can see, as we have seen in the slides also, this is the hidden Markov model. So the dynamic Bayesian network constitutes of two parts. First, base network, which is dynamic Bayesian networks. Second, this transition structure, which is basically the hidden Markov model. And if we do this n-1 times, then we will get the timestamps from 1 to t, which is basically our dynamic Bayesian network. So we see here that from this we can infer that we can divide the learning of the dynamic Bayesian networks into two parts. First, the base structure, and then the transition structure. So as we know, and as we move on this next slide, we will see that our structure can be known and unknown, and observability can be full or partial. So because of this, it gives rise to four possible combinations. So let's see them one by one. The first one is, if the structure is known to us and the observability is full, then we use a method called maximum likelihood estimation. Now what this is, so if we think about this intuitively, as the name suggests, maximum likelihood estimation does is it determines the values for the parameter of the model. What are the parameters of the model? The mean and the variance for in the basic, like for normal case. So the parameter values are found such that they maximize the likelihood that the process described by the model produced the data that were actually observed. So we want to make a prediction that, let's say in a linear regression, we have given a data points, then we want to make a line such that the observations occurring on it maximizes. So this is intuitive meaning of maximum likelihood estimation. Now coming to the second part, we have structure is known and observability is partial. Now if we use maximum likelihood estimation in this, then now we don't have values for certain parameters. So our maximum likelihood estimation will consider these as null values, which is totally wrong. And that's why when observability is partial, our maximum likelihood estimation doesn't work properly. So we need to do something more. So for this, we use expectation maximization. Now what this is is actually an iterative algorithm. What it does, it has two steps. First, the expectation steps, which use the observed available data to estimate the missing values, which was null considered in maximum likelihood estimation. Now the second step is maximization steps. Now we completely generate the data after the expectation step, and it is used in order to update the parameters. Now the parameters are got updated, then we again using this parameter compute the expected value of the missing data. Then we again change the value of the parameter depending on this expectation, and we go on till the model converges. And how can we see the convergence? Like the change in values from the timestamp t to t plus 1 is less than a value epsilon, which is set to 10 to the power minus 7. So this is how we can calculate the values when we know the structure, but the observability is not full. Now the third structure is unknown, and the structure is unknown, but we can fully observe the data. So in this, as the structure is unknown, we have to do this in two steps. First, we need to find out the local structures or the local minimas. Then using this local structure and local minimas, we need to model to calculate the global structure and global minimas. So this is how we'll do this part. Now the last part, which is when the structure is unknown and the observability is partial, then and after, like in the unknown and full one, after getting this, we can apply the maximum likelihood estimation, because the observability is full, so it will work perfectly fine. But in when the structure is unknown and the observability is also partial, first for the unknown structure we have to use the global and the local searches, and after that, as the observability is partial, we need to use expectation maximization. So these are the 4 cases which we need to consider. Now moving on to the next slide, there we will see that what the Bayes and transition network we talked about earlier are, like in more depth. So as I've like explained earlier also, that if we consider the Bayes structure, which was X, S, and E, we will be ignoring the temporal information. What are the temporal information? The state transitions from X timestamp T to T plus 1, and which it is equivalent to a Bayesian network. And from for transition networks, where we need to consider temporal information, we need to take 2 slices, which is xt and xt plus 1, and from there we can calculate the values, the transition probability matrix, which can be done using hidden Markov model. And we can learn the dependencies also at time t and t plus 1 using the Bayes structure. So I guess we are able to explain you guys what Bayesian dynamic Bayesian network really is. We started with the Bayesian networks, what it is. Then we saw why we need dynamic Bayesian networks, because the Bayesian network doesn't have a time parameter. But in real world scenarios, we do have a time parameter. Then we move on to dynamic Bayesian networks. Then we explained you guys about the inferences, different type of inferences. Then we got to the point where we know the structure, or we observe, or we can observe all the data or not. And at last we told you guys how we can we can form dynamic Bayesian networks using Bayesian networks and hidden Markov models. So that's it. Thank you.